I'm AKKOUCHE from the University of Constantinople. We are a small team working on quantum information and its applications. Today, I will talk about topological quantum computation. In topological quantum computation, we use the anions to encode and to manipulate the information. This is the outline, introduction, Fibonacci anions, some mathematical topics, pentagon, hexagon equations, Hilbert space dimensions, something. Actually, in topological quantum computation, there are many models, and many anionic models. And any anionic models have four properties: the topological charge, the fusion rules, the F and R matrices. Here, I will present the Fibonacci model. In the Fibonacci model, or the Fibonacci anions, is expected to exist in some fractional quantum Hall liquid at some specific filling factor. It's equal nu equal 12/5. This stated first time by Mead and Rizai. An anionic model also is a quasi-particle excitations of two-dimensional topological states of matter, which obey anionic statistics, not fermion statistic, not boson statistic. This is why we called anions. For Fibonacci model, the charge of the Fibonacci model, you can think about it as quantum spins. There are two particles, the vacuum or the trivial topological charge, and the Fibonacci anion, called 1 or tau. This is the fusion rules of the Fibonacci model. When we fuse two Fibonacci anions, we can get the vacuum, or we can get another Fibonacci anions. And when we fuse the vacuum with Fibonacci anion, we will get another Fibonacci anion. This is my mistake. This is another Fibonacci anion. And trivially, when we fuse to vacuum, we will get vacuum. This is how to calculate the F, the fusion matrix, and the rotating matrices. To assess the power of computational or of any anionic model, we have to calculate the braiding matrices, which give us the braiding properties. And to do that, we must calculate the F and R matrices. This is the two diagrams which represent how we calculate the F matrices. And there are a lot of calculation here, so I will pass. Physically, it doesn't matter to fuse the anions from right to left or from left to right. So this is physically equivalent. But in computation, it's different. This represents state difference from this. So there are two paths to going from this to this. By this way, we apply two fusion matrices, or by this way, we apply four fusion matrices. Here, I left just the non-vanishing terms. There are another term which is equal to 0. And by solving this equation, we'll get the F matrices in this basis. This is represented by the 0 state, and this is the 1 state, and this is the F, the golden mean, or the Fibonacci number. Also, this is another thing which I call this model as Fibonacci model. And also, when we exchange in these two quasi-particle, we will get this. We can think about this as states. States in quantum information theory or in computation, state like 0 or 1. This can be 0 or 1. And this can be 0 or 1 multiplied by matrices called the R matrices. And also there are many calculations here. We'll pass there actually. And to get the R matrices, we have to solve this equation and also we use the previous F matrices. The resolution, this is the same principle of the previous diagram. This is physically is the same of this, and there are two paths to go from this to this, and we'll get this consistency condition. And by solving this equation, we'll get the R matrices in the same basis, 0 and 1. In topological quantum computation, we encode the information in the word lines of particles, not in the particles themselves. So this matrix represents this braiding. This is where we encode our information. We pulling out from the vacuum quasi-particle, and we do our calculations and our braiding, and after that we do the measurement. So the external perturbation can do that because we are encoding the information in the topology of word lines. So by using some properties of knot theory and like Redminster moves or a polynomial of Jones, we can get the original state. So this is why the topological quantum computation, it's resistance against the decoherence. This is the procedure of our work. We create quasi-particle, we encode the information, and we do the measurements. This, the enclosed of the overlap, take the charge of the particle enclosed within. When we enclose the vacuum, the charge is 0. But we enclosed a tau or Fibonacci anion, the charge is 1. But when we enclose two Fibonacci anions, I don't know. This depends on the fusion rules of each anionic model. In this case, the result can be 1 or 0. So we can encode our information this. We can, when it's equal 0, it's 0 bit, and when it will equal 1, it's the 1 bit, and this is my qubit. But when we use two Fibonacci anions, there are problems. When we apply my braiding matrices on this qubit, I will, for example, when I apply my braiding matrices on the state 0, I will stay in the same state, 0. So I will don't have a superposition between 0 or 1. And this is two-dimensional Hilbert space. The solution is to increase the number of Fibonacci models. For example, when we use 3 quasi-particles, I have 3 possibilities. When we fuse this and this, I get 1, and I will fuse 1 with another. I have 2 possibilities, 0 and 1. And the third possibility is this give us the vacuum, and when I fuse the vacuum with another Fibonacci anion, I will get the 1. This is 3-dimensional Hilbert space. This state, I will refer to this state as the 0 bit, and this is as the 1 bit. And the third state, I will call it to non-computational state. And when we apply our matrices on this state, the transition to this state, it's not a good thing in quantum computation. This leads to leakage error. Some of information lost. And there are general rules in topological quantum information. When we do the braiding inside a novel, the topological charge doesn't change. But the problem happens when I work in 2 qubits or more than 2 qubits. So this is the dimensionality of the Hilbert space. When I use, you can see that here. For example, when I use 2 quasi-particles, the dimension I can represent it by the number of paths, which lead from the point 0 to this point, represented by the charge and the number of quasi-particles. For example, when I use 1 quasi-particle, the dimension of Hilbert space is 1. When I use 2, the dimension is 2. When I use 3, the dimension is 3. And when I use 5, the dimension here, 4, the dimension is 5. When I use 5, the dimension is 8. So the dimension of Hilbert space increases as the sequence of Fibonacci. This is another thing why we call this model as Fibonacci model. We can think about the quasi-particle as a group and the Braden matrices as the generator of this group. So by using the F and R matrices and do some calculations, we'll get this Braid matrices. This Braid matrix is topologically equivalent to this. And by putting this together, I will encode our informations. So this is why. This is our state. I use the sigmas matrices to encode my information. So to get in a single qubit gate, I have no problem because I do the braiding inside a novel. So the total quantum charge doesn't change. One stay always one. So there is no transition to the non-computational state. So there is no leakage error. And do some programming codes like brute force search or bidirectional search or quantum random walk search or any programming code. We'll get these sequences. And this is actually the challenge. When we get this, I get approximated. For example, we use this braid to approximate the unitary gate or to approximate the Hadamard gate. The trace distance between the unitary gate and the approximated gate is of order 10 minus 4. And here for Hadamard, I get for 10 minus 3. This is a good approximation. Also, I will pass to 2-qubit gates. In 2-qubit gates, I will use 2 qubits. So the braiding pull out from 1 qubit to another. So I don't know what's the topological charge of the final state. And in this way, the leakage error happen. And also there are problems. The brute force research or any quantum random quantum walk here doesn't work in this case because I have 6 anyons and 5 braid generators. And 5 braid generators is a huge number to do a brute force. At this stage, it's useful to introduce another notion called the weave. In the weave, there are only a single quasi-particle move. This mobile quasi-particle is called the weft, and the other two, the static quasi-particle, called the warp quasi-particles. So this is counter qubit. There are many tricks to do that. Actually, not many, just three tricks to do that. I use the injection-based waves. Here, I use the unitary gate. This is okay. I inject the unitary gate. When we apply a unitary operation, it's like we don't do nothing. The idea is to put this control pair here inside the second qubit. And after that, we do the rotation or the encode of information. And I will encode my information in the second qubit. So in this trick, there is no leakage error because I encoded, the information is encoded just in 1 qubit. And the third step, I will do the extraction is the inverse of the injection. And the two pairs or the two control pairs return to the first place. This is other 2 qubit gates. This one, it's used another technique, mathematically pure. And this is how to build the analog topological analog for quantum computation. And I think the topological quantum computation is promising model for universal quantum computation. And thank you.